talk about, I've got two main things to do. I want to talk about a comb filter, and then I also want to talk about deconvolution. I mean, we know what convolution is. This is sort of the inverse. Really, I'll tell you the truth, it's very easy and simple to understand. You're just going to take whatever the filter transform is and take 1 over that to find out what the actual, if you have a y of n or a y of z, and if you want to know what x of n created that, instead of having an h of z, you take 1 over h of z to put it in. So it's very easy to understand. And if time permits, I'd like to get through to windowing too, but I'm not sure I'm going to get to that. Has anybody, did you have windowing yet or no? Any of your laboratory work? Mm-hmm. Okay, well, we'll get to that. Now, before I start, this Friday is a test, right? Mm-hmm. Now, I want to make sure everybody's on the same page on this one, that we don't have anybody that doesn't know it's coming. All right. What I'd like to do next class is take some of the class time to review and answer questions. Now, I'm going to tell you this right now. Because of the breadth of the amount of material, all right, it's going to be focusing on everything. Most of the test is from the actual, where the last test ended till now. Now, there's material that overlaps both. Do you follow me on this? Like, you have to understand Fourier transforms and Laplace transforms to appreciate and understand how to do things like the bilinear transform. You can't do them without understanding Laplace. So your knowledge of that is expected. You can't just assume nothing like that is going to be required. But by the same token, the majority of the focus is on the newer materials. Z transforms, DTFT, DFT, and all the applications therein. Does everybody follow me on this? So if you're studying now, I'm encouraging you to go through the homework since the last test and make sure you know how to do them. And if you have questions on Wednesday, bring them. Do you understand? I'm trying to be as clear about this as possible because this is a tough test. The second test and the final is obviously the most difficult, but usually people by that time, if they've really been studying and keeping up with it, on the final exam, I get a whole bunch of very, very high grades. By the same token, I also get people that fall off the map, low grades, because, and there's not a lot in between. This class has, it's sort of it's not really a weed course, but what it does is separate those that are serious about engineering and those that aren't. That's my opinion. You're all smart. You got this far, you're smart. Now you're going to find out who's willing to apply and really focus on this stuff, because it is difficult, and there's a lot of it. All right. Any other questions? Yes, sir.
You have last Friday's quiz, didn't you?
Got it in my office upstairs. Honestly, I grabbed that one out of my box. I don't think I have it with me. If you didn't get it, I gave back a bunch of them to the people that follow me upstairs. If I do, I'll hand it back. That's the current quiz, right? This is today's quiz. I mean, excuse me, last Friday.
Oh, you're already. Right, okay.
Let me just do this book in here. I take it back. I have some. Tell you what, I'll put this one too. This is, I think, 2 Fridays ago. All right, now, check through it because I've got some other stuff I threw in this one that had, there are people that didn't pick up their homeworks, tests, stuff like this, so I threw it in there. So go through it. If you've been missing a few things, take a careful look through there. And I'd like you to, when these get to the back of the room after everybody gets done, please make sure that pile gets back up to me. I think one pile was left here by mistake. All right. Okay, any other questions about this? So what we did last time, what we've been focusing on is filtering. We did the notch filter, right? Just quickly, I'm going to just tell you, if you want a notch filter, we're going to be using this. What we're really talking about is this. If this is omega here, we're talking about a notch filter, this is h of omega. This was shown wrong on the actual graph when I was doing the presentation. It's right on OneNote, but I showed you the inverse of this by accident. But a notch filter should do this, should be about 1 all the way to the point where the notch occurs, and it should just stop that frequency. That's a notch filter in a nutshell. Does everybody follow me on that?
Yep.
Now, something else. If you take 1 over this, instead of a notch filter, you get a pass filter. You basically are passing everything. Excuse me, you get not a notch filter that stops it, but you're just passing this frequency band. You follow me? So if you looked at this and you wanted a, I'll call it a band, a very narrow band pass filter, you would take 1 over h of omega of the notch filter, call it h of n, that being notch. And then you would get this. You would basically kill everything except at the notch frequency, and then you would get this. Follow me? You would only pass that frequency. This could be used for like tuning for a signal. You know, with AM, FM radio, you're basically tuning up and down the dial to allow that frequency only to be really demodulated and then amplified. Follow me on this, class? Now this is why these things are real important. For the notch filter, remember the way we actually defined it. We said h of z, and I'll call it for the notch, was equal to really z squared minus 2z times cosine of omega I plus 1 over z squared minus 2az times cosine of omega I plus a squared. And that would give you it. Now a, for the notch filter, magnitude of a is less than 1, or else you basically just get everything passing. But the reason you have that there is so the reason you have this lower part, the denominator, is so other frequencies aren't adversely affected. That's the reason it's there. Everybody got that? That's the reason. Now, taking that into consideration, here's the next kind of filter we're going to talk about. It's called a comb filter. And I'll tell you why it's so important. Let me tell you one other thing about this. The filters I'm selecting to spend time on are things that are very useful in the real world. I can only tell you that people that I know, especially small companies, when they hire someone like yourselves, you become automatically a jack of all trades for a small company. And that's where really you're going to make a lot more money potentially than in a large company because of growth and things like this. And I can tell you from personal experience with people, I've had students sitting where you are, who went to graduate school here, one in particular, and I'll use his name, Dan Fairclough, and then started their own companies after they worked for a few years in industry. They made a whole lot of money, but the thing that it requires is that you become a jack of all trades and a master of several, where you have to be good at everything. When you're programming microcontrollers, my wife's doing some of this right now, that's the reason I'm going to mention this. You're programming microcontrollers to do digital signal processing. Do you follow me on this? That means everything I'm showing you, the notch filter, the filter you're going to see today, comb filter, all those are very useful. And I'll tell you why. There's an evil menace called 60 hertz out there. Now, has anybody ever had any kind of 60 hertz hum in anything? You know what I'm talking about? You have? Does anybody else? It's the most annoying thing, and it's everywhere. Not only is 60 hertz there, but all its harmonics. 120 hertz, 180 hertz. All these other harmonics, anytime you have anything that takes that and rectifies that and makes it into a DC signal, you get these other harmonics that are all over the place. And it is just a pain in the butt. So the way to get rid of it is with cheap filters. The cheaper the better. In the old days, we had analog filters. You've probably heard about LC circuits, tank circuits. Well, you could tune a tank circuit, either in series or parallel, LC in series or parallel, to discriminate and either stop that frequency or short it out or both. Do you follow me? Now, those things work, but I want you to know something. They also have a problem. There's a lot of problems with the filter itself causing unwanted effects. I can't get into all of this now, but it will have a detrimental effect on other frequencies. These filters don't do that. They're very, very good. If you all remember that notch filter, how sharp it was, these are phenomenal. So now with the comb filter, let me go through this, and I chose this because this is a real world scenario. So in the comb filter, you can do it 2 or 3 different ways, 2 ways basically. Suppose I had 3 frequencies I wanted to get rid of. If I had 60 hertz, all right, in the book he talks about this, I have 120 hertz signal, and I have 180 hertz signal. And I want to get rid of all those frequencies, but I want to pass 30 hertz. So I want to pass 30 hertz. These I want to eliminate. All right. Now, I'm going to use a digital filter to do this. So there's something, I'm doing what the book's showing you, and I'm going to show you how you can use a comb filter to do this. It'll be obvious. But the book says there's going to be a standard sampling frequency, and it's going to be 480 hertz. So that's given. All right. Those are the frequencies, and these frequencies are in hertz, but that's the sampling frequency. So one way to get rid of all those 3, so you've got 60 hertz, you're going to have the harmonics. You're going to have 120 and 180, all right? One way to get rid of these is just have 3 standard notch filters in series. Do you all agree with me? All for the different frequencies. So one way to get rid of this would be this. Call it H1, H2, and H3. And here comes the output. And these could be realized by standard microcontrollers or really microprocessors. And now we've got the input signal here. This is X of T. And X of T has all these frequencies, and they're sinusoids or cosinusoids. And they also want to pass this frequency. So I could say H1 is going to block 60. H2 is going to block 120, and H3 is going to block 180. I'll only just do one of these just to show you one frequency. It just repeats itself. Now, the value of A is something you're going to learn more about in your controls classes probably, and if you take DSP, digital signal processing, or digital image processing, you'll learn a lot more about filter selection, how to do it. But in general, you're going to make A about 0.95 or better, something like that. That, remember, the higher the value of A, the narrower the band is, right? But there are some problems because if it's too narrow and there's any jitter in the signal that you actually want to filter, you'll miss it, if you follow me on that. Remember, these things, we always assume the ideal. We assume it's always going to be at that frequency, and there's no wobble to the frequency. Well, that's a falsehood. There is. There always is. All right, so if I'm just going to do this one, I want to create a filter, a standard notch filter to block that one. Let's do it this way, all right? If I'm going to create a standard notch filter for that one, we just did this. What do I do? Remember the steps? Well, I want to block what? 60, right? So I want to stop 60. So I want to block 60 hertz. Next thing I find is omega I, right? What is omega I? It's 2 pi, right? 2 pi times the frequency I want to block, correct? Which would be 60 in this case. Now, normally it's multiplied by the sampling period, TS. But that's the same exact thing as dividing by the sampling frequency. Does everybody understand that? The period is inversely proportional to the sampling frequency. So you might as well just put Fs down here, right? And therefore, omega I here would be equal to 2 pi times 60 and divided by 480, right? So that's going to be what? 8 times 16 pi, isn't it? Am I right or wrong? Oh, wait, I'm way off. That's what? That's 2 pi over 8, isn't it, class? So it's pi over 4. And that's radians per second, technically. Follow me on this? It is an angle, but I put per seconds there. Do you all see this? Now we have that. So now we have the argument of the cosine term right there. And I can do it. I'm just going to put this. Now I can say my h of z here would be equal to z squared minus 2 times z times the cosine of pi over 4, which is what?
1 over square.
It's 1 over square root of 2, right? And then it's going to be plus 1 over z squared, right? Minus 2 over the square root of 2 times a, and I've made my a 0.95. And then it's going to be times z plus 0.95 squared. Are you with me? I'm going through the motions on this one. This one's going to have a middle term. It's not going to drop out. Does everybody follow me on this? The cosine of omega I is not 0. Follow me? This is the reason I'm doing this one, because now it's not dropping out. All right, now for that one, you can obviously see that what happens, I'll come back over here and do it. All right. Now I got what? I have h of z equal to z squared minus 1 over the square root of 2 times z, right? Plus 1 over, yeah, right? Over z squared minus 0.95 over the square root of 2 times z plus 0.95 or 0.95 squared. Now I have my h of z. Does everybody agree with this?
You dropped some twos.
At what?
Twos.
Well, 2 divided by square root of 2. Oh, square root of 2 on top, my bad.
Yeah, just-
Square root of 2 on top. That's my bad. Square root of 2 on top.
Oh, yeah, you're right. Yeah, 2 over 2 is root 2.
Okay, thank you. Right? Now that I have that, the next thing I need is a difference equation. Do you all agree with this, class? So we all
Yes.
know. All right. If I want a difference equation for this, I know that this itself is y of z, right? I mean, I could do one other thing. Couldn't I put the z equals e to the j omega, and I could get literally the defined filter response, correct, class? Does everybody see that? If I let z equal e to the j omega, you could get then the definable filter response, and you could actually plot that. Go ahead.
I think you just
Here, oh, that's 0.95. You are so right. I'm trying to. Sorry. Does everybody see what I'm up to here? Now, if you wanted the filter response just for completeness, I could put h of z equals e to the j omega, and then you could plot this from minus pi to pi, plot the magnitude. Do you all see that? And we already know what the filter response is, don't we? We've already got a notch filter. We know what's going to happen, right? And really, if I left it in terms of a, we could just make a closer and closer to 1, and you see a very deep notch. All right, but we don't want to make it too deep, because then if the frequency we're trying to eliminate's got any wobble at all, we won't get rid of it. So now I'm not even going to bother with that part. I want the difference equation. That's what I'm up to, and this is y of z over x of z, right? We've done this before, but I'm going to go ahead and let y of z on this side, and that's multiplied by z squared minus square root of 2 times 0.95 z plus 0.95 squared equals x of z, z squared minus square root of 2z plus 1, right? And the next step is, now I've separated them, so I have x on one side, y on the other is functions of z, and they're all times power, z to some power, all the way down. The next step is what, just to be sure everybody's got it. We want to make sure we divide by the highest power of z, don't we? So we're going to divide everything by z squared, and in doing so, now I have y of z times 1 minus square root of 2 times 0.95 divided by z plus 0.95 squared over z squared is equal to x of z times z squared, times 1 minus the square root of 2 over z or z to the minus 1, plus 1 over z squared. And this is just like z to the minus 1, z to the minus 2. I chose to write it that way for no other reason than I felt like. Last step is what? We want this as a difference equation. Remember, a real-time difference equation is easy to implement. You only need a little memory. You keep track of only a few numbers before, right, x and y, and we predict the next value for y. Do you follow me on this, class? Remember, the clock cycles are really the values of n. Think about this. Every time you go through a clock period, that would be like incrementing n by 1. Everybody understand this? So this is a very easy, it should make sense to you how a microcontroller could do this. You have done something with microcontrollers, right? How many have?
Not filters, but that sounds.
No, you've used a microcontroller. How many have at least dabbled with a microcontroller? How many have not? Really? I thought you guys got microcontrollers up to this point.
We haven't.
Computer systems is the only class that goes into them, and you only use a simulator.
Oh, you don't actually?
Yeah.
You had one.
Did you have a lab with it?
With Lee, you
Unless
only
you have a
use
good test.
Wait, what?
Nelson didn't give you a discovery point.
He gave you what?
He gave you a microprocessor.
What
doesn't
course
give
is
you
it?
It's computer system.
What-
Dr. Nelson gave us microcontrollers. to
But
use,
what
and
course number?
22.
It's, all right, it's concurrent, and this is the year you should have that, all right? You should be exposed to these things, that's what I'm told, all right? If you haven't been, you should be soon, all right? Because all this stuff goes together. You know, with your circuits, you basically had a course in circuits, right? RLC, and you did both what? Transients, first order transients, and you did steady state, correct? And then you had a lab that actually showed you in the laboratory all the circuit's performance characteristics, right? Correct, class? How many have had op amps here?
Now we
Outside of this class, no.
This is coming up next. You're also going to have microcontrollers. Everything is going to come together. Everything. And you should be, by the time you get out of your junior year, you're really familiar with a whole lot of stuff if you co-op that they'll be thinking you're like a normal graduate would be at that level of understanding when he's gone through a senior year. But after your junior year, you should have all this stuff down if you've done it in sequence the right way. Now, last thing we have to do is take this and put a difference equation, right? Let's go ahead and just do it for the record. We have y of what? N, right? Minus square root of 2 times 0.95 times y of and minus 1, just making sure. And finally, plus 0.95 squared times what? Right, this is going to be important. We'll see why in a second. But I'm doing this. Then I'm going to get that equals x of n minus square root of 2 times x of n minus 1. And finally, plus x of n minus 2, correct? With me? That's the difference equation we're going to implement. Now, I want you to just take one look at this and notice here we're going to take that y of n on one side and everything else on the other side. You follow me? Now, think about the amount of memory you need. You're going to have this term in memory, right? That's 1. This term in memory, 2. This term in memory, 3. This term in memory, 4. And this is the input. So that's not in memory, it's incoming. So you have 4 bits of memory for that filter. With me? Now, you're going to have 2 more filters in sequence, right? That are stacked in sequence like that in series. And that means you're going to have 4 times 3 or 12 memory items that you have to access and pull back every clock cycle. Follow me on this.
Yeah.
Now, that doesn't seem like a lot, but what if all of a sudden with this thing you don't have 3 harmonics, suppose you have 33 harmonics. Where I'm going with this is when you have square waves, a lot of times you don't have 1 harmonic to worry about, you have a whole lot. And that's why comb filters are necessary, because they work at the harmonic, but there is an easier way. This is where I'm going with this. This is perfectly acceptable. So only those 3 frequencies you're worried about, this works. But many times it isn't just 3, it's a lot more. And they're periodic, so you want something that would eliminate all these problem children. And that's where we're going next. And but this doesn't always work. There's certain conditions where I'm about to show you. Remember this for small companies. If you get it in a small company. is there a course that is available to you, doesn't have to be in this department, on really, I want to use the word, on developing a small company, but it's really on like a small business model? Does anybody take this?
That would be cool.
I think I've heard that there is. I'm trying to think if it should be in the College of Business, but it might be in somewhere else, might be in industrial engineering.
There's a business technology minor.
Well, it should be a course in like
It's probably in there.
entrepreneurship or something. Is anybody taking this?
This is a good personal finance book.
Don't worry about that. I'm talking about how to build a business. Engineers oftentimes are oblivious to the importance of understanding finances and laws, business law, because a lot of you sitting here are going to be either in small companies or starting one at some point. I know this for a fact. It happens every class. I look back, and when I see them at tailgates and stuff, when they come back 10, 12 years later, they always introduce themselves, and they're either working for, they're higher up, or they own a small company. But the problem is, you aren't taught that. I think it's a course in entrepreneurship. Take a look next time. If you get a chance to take that, try. All right, it'll help you immensely because it'll expose you to the laws and everything else. I'm telling you this. You know, you don't pay for this kind of advice, but I think since so many of you are going to end up there, you might as well just get ready for what you're going to need to know. All right, now here's how we can do this with a single filter operation if certain things happen. This is important. This is another way to do this. And first I have to say that there's one condition. We have to take a look at the sampling frequency. Really, let me just tell you this. Suppose we have suppose we want to get rid of 60 hertz. Listen to me now. And all its harmonics. Oh, yeah.
So the problem you just did was a cascaded notch filter, right?
Mm-hmm.
At 60, 120, and 180.
That's
And the
right.
book solution is very much more complicated than yours.
No, it actually, there's two solutions. The one I gave you is one of the book solutions.
I'm looking at both. You're about to do the second one, right? And the first one has more terms than your solution has.
Well, it does because I only did one filter, right?
Okay.
There's two other ones.
Okay,
Remember, I
that's
just
what
did the
wanted to
60.
Make sure.
I said it would be the same for you for the 120 and for the 180. Does everybody recognize that? So then you would have to take those three filters, and you would have to take the first filter, cascade it into the second, cascade it into the third. All right, and if you wanted a single H of N, right? I just got you the H of N for the first one, so you could run that one first and have the output of that one feed the second. Then the H of N of the second and feed the third. Or you can get one big giant H of, you could get one big giant Y of input, from the last filter to the input for the first filter. And then you're going to have a whole lot of terms.
Okay.
Do you want to do it that way? You gotta-
No. I just
It's
wanted to
easier
make
this
sure that
way.
we had actually skipped.
What he's saying is this. I have an input-output for only one filter, right? The output of my filter feeds the next filter. Follow me on this? And then the output of that filter feeds the next filter. So I have three separate difference equations. His book has one big monster difference equation, right? Where he takes H1 in Z, H2 in Z, and H3 in Z and multiplies them. You follow me what I'm doing here? And so he gets terms that have Z to the 6th, which means he's going to have to take N minus 6 type terms. You don't want that. At least I don't want it because, frankly, it's just too messy. I mean, you can do it that way.
Yeah, I just want to make sure.
But my real point is that there's a lot of memory involved. That was the whole point of the way I did it. You're absolutely right. You can do it that way. Here's the second way that's easier. If certain conditions happen. And this is the condition. If I have I'll do it his way. The sampling frequency divided by the actual frequency you want to eliminate. Now, Fs for this one is going to be the sampling frequency. Now, sometimes you can't choose that. Sometimes it's given. And I want to tell you, for clocks, a lot of standard chips that you buy, the sampling frequency is going to be the clock frequency, and it may not be tunable. However, if it's tunable, you're in luck. You can always do what I'm about to show you. If this is an integer, this has to be the case. It has to be an integer. Then, and we'll call the value n naught. Then what you can say is, now I'm going to get, what I'm trying to do is eliminate f naught. That's what I didn't put down there. We want to eliminate this. We want to eliminate that frequency, just like we wanted to eliminate 60 hertz before, all right? That's the frequency, but this will get rid of the harmonics too. It'll get rid of 60, and it should get rid of 120 and 180 and all the way up the line, one filter. Now, when we look at this, the way they're going to say to do it is, if this is an integer, and if it's not, you can't do it this way. Then you need to cascade it like I did. If it is an integer, then you can have this equation. You can say that y of n minus a to the n naught. Now remember what n naught is. And here a has got to be magnitude of a is less than 1. And it's going to be times y to the n minus n naught here is equal to x to the n minus, and then it's going to be x to the n minus n naught. Now, I think his book does use n naught, but if it doesn't, let me know. I'll change it.
It uses it.
All right. And I'm going to go through the Z transform this and show you why it works. Now, this, of course, I wrote in terms of a difference equation. I just stated that. I didn't prove it. I didn't develop it. But if we take a look at the Z transform of this would be y of z, right? Then it would be times what? 1 minus a to the n naught, right? Times z to the minus n naught. You all follow me what I'm doing here? Because there's a delay of n naught. It's y minus n naught. And n naught has to be an integer. All right, times y. It's this times y of z is equal to x of z times 1 minus, and this would be z to the minus n naught. Now I hope you see that this is the Z transform of that. Nothing more. Now, when I go ahead and take a look at this, when I take a look at my h of z here equal to y of z over x of z, what I end up getting is going to be 1 minus z to the minus n naught over 1 minus a to the n naught times z, right, to the minus n naught. I'm just restating it. And then I'm going to multiply top and bottom by z to the n naught. And I end up getting z to the n naught minus 1 over z to the n naught minus a to the n naught. So everybody follow me on this. This will make sense to you. I want you to think back just for a second before I keep moving on in there. The way we found out how come that other filter worked, the notch filter. If the cosine term wasn't there, we had really z squared plus 1 over z squared plus a squared was the h of z for the notch filter. Do y'all remember that? That's if the cosine went away. If we made omega I pi over 2, right? Do y'all remember this right here? Now look at this one. That's not that far off. It's different. For this to be a 0, what did you know? That z squared plus 1 is 0, or z squared had to be equal to minus 1, right? And we could figure out where the zeros are for that. And we're a conjugate pair, right? Now look here. Where are the zeros for this one? Because we want the zeros.
Z and naught.
Zeros will be with what? Z to the n naught minus 1 equals 0. Correct, class? Now, follow me on this. What is z in terms of a filter? Well, z is e to the j omega I, right? Or omega. Let me just leave it as omega, correct? Now think about this. We're sampling, right? Something I failed to say. This is also the period. Or it's the period of the waveform. It's periodic with n naught when you sample because of this condition. If you read the book on this, he goes through it and gives some details of it. But really what you have is a waveform. We have a waveform we want to get rid of f naught. we sample it much faster than F naught, all right? Now, if that sampling is such that there's exactly an even number of samples used to sample that waveform, then we can say that the number of samples would be Fs divided by F naught. Normally it's done by what? T, the period, divided by the period of the sampling waveform. That's the way you usually get this. But because the period and the frequency are inversely proportional, I put the sampling frequency on top and I put F naught in the bottom. Does everybody follow me on this? So you perfectly sample it, so you do this and it repeats itself every time. The periodicity is going to be, therefore, the period will be N naught. That means if I take this, since it is periodic, it will be e to the j 2 pi over N naught, right there. And it's going to be times k. And if you look at this, remember this is like, because it's sampled, all right? This will now be at these frequencies, 2 pi N naught over k. Do you follow me on this? It's not continuous frequency I'm worried about. We're sampling it. Do you follow me on this, class? Now look here. If I put this for z, I have what? E to the j 2 pi over N naught times k, right? But that whole thing is to the N naught power. What happens? N naught cancels, doesn't it, class? What do I have? I have e to the j 2 pi k. Well, what is e to the j 2 pi k when k is 0?
1.
When k is 1? When k is 2? When k is minus 1? Always 1. Follow me? And then you have what? You have 1 minus 1 is 0. In other words, you have zeros there. And that's what you want. You want the 0. If this is an integer, you want to get rid of this frequency. Right? I'm sorry. Rid of F naught. If it's an integer value, then you can with just this. And not only that, it gets rid of all the harmonics. Because the harmonics are going to be at what? Not at F naught, at what?
And 2 F naught, 3 F naught.
2 F naught, 3 F naught, and they're always integers there, and they always land on top of this notch. It repeats itself and it gets rid of them. Do you follow me on this, class? Now, what about this filter right here? How many terms do I have there to keep in memory? N naught is given. Follow me? If you have a signal and you're sampling at a certain rate, and you know the frequency you want to get rid of and any harmonics, well, here I only have what? 1, 2 memory items plus an input. Do you see what I'm talking about? How many do? What are you looking at me like that for?
Well, you can't implement it with only 2 memory stores. You have to store everything back to N minus N naught.
Well, actually, this is a delay. All right? Now, the thing is, when I take this, right, and I store it, you're absolutely right about, I know where you're going with this. You have to store, if you wanted to do this in real time, it's sample. These are the 2 values you're going to be using, right? But if in the next one I take a look at, then it would, when n goes to n1 here, I mean it's n plus 1, then you need to access n minus n naught plus 1.
Right.
So you could start it, but there's a clever way to get around this. This one, I'll tell you, at least with real-time processing, this is much easier because you're only accessing 2 samples from memory, and you're doing simple arithmetic operations. By the way, this is not an arithmetic operation, that's a constant. You can just call that a value. It's a to the n naught always. Follow me? This is easier to do. There's less number of calculations. Later on, you'll see that the number of calculations, it becomes critical in clock cycling when you're doing it, because you're going to reach a limit for how fast you can do certain things on chips, especially the more inexpensive microprocessors. I don't know a lot about microprocessors, I'm just going to confess that. Arduinos, you guys use all the time, Ryan? You don't use it. I mean, who's familiar with that term?
I used to.
There's a lot of different microcontrollers out there, and and you want to use the least expensive one possible that can do the job, because with companies it always comes down to what you can do for the money. If you work for the government, then you don't worry about it. And I'm not kidding about this either. But if you're working for yourself and trying to make money, you do. All right, those are the filter items I wanted to go through. We can do a couple of problems with this if you want. You are right about one thing, though. He said this, that has to be stored, the past values through and not, for both x and y. The real calculation is only going to be required 2 of those values to be accessed. All right. Give me 1 second. All right. I think, do you feel that you can just handle a couple of problems with that on your own? If I give you solutions? I think you can. It's not hard. It's just an extension of something you already knew. And if you do it for the using cascading filters, don't write the whole equation down in terms of z to the 6. Just do individual difference equations. We know we're going to multiply, or we're going to have one feeding the other. It's easier that way. The next thing is deconvolution. Now, in his book, he talks a little bit about deconvolution. Here's what it means. You know, normally you have x of n, and it comes into something that has a response h of n, and you get a y of n, right? Well, I want to tell you what this actually can represent. Y of n would be the convolution of x of n convolved with h of n, or vice versa, h of n convolved with x of n. Now, what this can represent, though, is a sensor. This could be a sensor of some sort. And here you're reading the output of a sensor. Now, you may not be able to alter the design of this sensor. Try to understand this. There's a lot in this one. Dr. Dean does a lot of stuff like this, where he has sensors that have a certain input-output relationship that he can't really do much about. He's got to work with it and try to figure out what the input was that created it. But he can read the output of this filter. What he'd like to do is be able to figure out what the input was, and that's a reasonable request. If it's a pressure filter and you're measuring a voltage output, the voltage isn't the pressure, but you can infer what the pressure is if you know the relationship between pressure and voltage. That should make perfect sense. And there's a million other filters. So if you look at this in terms of an x of z problem, with an h of z, rendering y of z here equal to x of z times h of z. This works also for continuous time, but we're in discrete, so we're going to do it this way. What we can say is, if I have this right here, and my goal is to get x of z, then it makes pretty good sense that what I need to deconvolve it is simply taking my y of z here, which is x of z times h of z, and just putting it into a filter that has the response 1 over h of z. Because then my output would just be x of z. And that should make perfect sense to you, right? Now 1 over h of z can be rendered in terms of what? A difference equation. Do you all agree with that? So can h of z. Here's the problem. This, in order for this to work, it has to be BIBO stable, or it has to be bounded input, bounded output stable. What it means is, when you look at h of z for 1 over h of z, the poles, all right, have to be inside the unit circle. Do you follow me on this? It has to give a stable response, or else you're really in trouble. It also has to be causal. It may not be. You know what causal is, right? Everything in the output is dependent on the input or past values of the input. It can't predict what the input can be. So you got to watch out for causality too, doing it this way. Now there's something else I'm going to tell you. What you really try to do when you do this stuff, you really want this guy here to behave a finite input response filter. Remember what a finite impulse response filter was, where you had a finite number of h terms, right? Do you remember this, class? You didn't have an infinite number. How many remember that? I'm going to go over that next time. But finite impulse response filters are beautiful because they have a finite number of h of n's, right? I mean, the h of n is limited, and then 0 beyond and 0 before 0. Those almost always work, to the best of my knowledge, when you do the inverse. But when you get unbounded ones, you get problems. Because usually if one's stable, the other is not stable. Because the poles are inside, or if their poles are inside the one circle and one, when you take 1 over at, the poles are outside. Do you follow me in this class? So you got to be real careful for infinite impulse response filters. I'll give you some homework. Come with your questions next time when we talk about the test. Take care. Now, are there extras back there, the tests and stuff? Were they all taken? Fantastic. Is everything good?
Very good.
Take some of the last answer. Let's see.
You're just writing normally.
Comparison of VFDs, we didn't do Z-transforms, we didn't
The design.
you have to access these.